Okay, so welcome back. And today, now in the second session, we will discuss something related to how we are going to implement the things that you learned in the session one with IBM Qiskit. And I will let you know what IBM Qiskit is and then how we can use that to do some interesting applications that might make you interested into some more interesting stuff later on. So before moving, okay, before moving on to the session, I will say something about me. I'm a PhD student in electrical and computer engineering in Cornell University. And before joining for my PhD, I was a lecturer on contract at ENTC, University of Moratuwa. And before that, I also graduated from ENTC, University of Moratuwa, from 14 batch. So if I say about my research interest as a PhD student, in earlier days, like when I just started my PhD, it was more of information theory and privacy and security in the classical world. But last year, I was able to get to know some things related to quantum information theory, which led me to work on those projects as well. So currently, I'm working on projects related to quantum information theory and how they are related to some quantum privacy models that are quite involved these days. So I would start my session and with what we can do with the quantum computing and show you some interesting applications based on what I have learned so far, and I'm also learning throughout this journey. So if you have any questions, you can ask, because when I just started, also I had a lot of questions and I still have some. So you can, I'm sure that you may also have questions, so you can definitely ask them. And then if I know them, I can help you with. If not, there are other instructors also, they might also help you with those. So let me get started. So what we are going to discuss today is based on Qiskit and how IBM quantum experience is to be. And then we will try make the first circuit in Qiskit, which is like the hello world in any kind of coding, when you learn any kind of coding language. And then we will talk about two interesting applications. Like if you remember from the previous session, we were talking about some things about exponential speed ups and certain things. So we will see a simple example like an algorithm where the quantum speed up can be achieved. And then we will talk about quantum teleportation and entanglement. So you might have heard these words in the first session. So knowing a little bit about this, like the words itself is enough, and we will go through what we can do with this using IBM quantum experience tools. So this slide also might be familiar to you from session one. So even though we are talking about IBM and Qiskit, there are several other tools developed by several other companies in making this quantum computing more useful. And then this is more helpful in the sense, like you might not have a quantum computer to begin with to start something on your own and trying something. But here the IBM Qiskit or Google Search, what they are giving us is an opportunity to try our codes and try our quantum algorithms that we think of on their quantum devices and discover new quantum algorithms on the way. So this is an opportunity that we can take on so that we can use those quantum computers that are available now, which has limitations, but we can use those computers and quantum devices and see whether we can use those limitations still by, even though there are limitations, we can use those for several applications. And earlier we didn't see what Q Sharp and Microsoft is doing. Microsoft is also having a platform more on Q Sharp and Quantum Development Kit. It is more close to C Sharp rather than Python, but it's worth to mention that the Quantum Development Kit has some ways which even Python codes could be incorporated in the recent ones. So it might be a useful tool in some applications as well. So as you have heard from the beginning till now Qiskit is a IBM's quantum computer programming language, and it's an open source quantum computing software development framework. So as it is open source, we can try to use them to learn as well as to come up with something new. So when talking about IBM Quantum Experience, there are two kinds of tools that you can try. One is IBM Quantum Composer, which is like a graphical building model. I will show you when we start the thing what it is, and I think Kitmin just showed something related to the graphical model. And then we will work more on IBM Quantum Lab, where we can use Jupyter notebooks that you are using to code Python, code in Python, and see how we can use those to code and to run quantum algorithms in IBM quantum devices. So when talking about what kind of quantum devices available, in Qiskit, we have two types of things that we could run a code. One is a simulator. So this simulator is basically made up with considering the mathematical structure of things. So it's like, if you could think of it, it's like the ideal quantum computer that one would be targeting at. And then these simulators are helpful for us to debug and validate our circuits before sending it to a quantum device, because the quantum devices are expensive to make with and to use them. It might take, sometimes you have to be on a queue to get your turn. Even though your code will run in a short time, you have to be on a queue to get the service from a quantum computer. So it is better to simulate and debug your code using a quantum simulator, which is there in Qiskit, and then run those things in the quantum computing resources of IBM. So I have some of the things that some of the IBM quantum devices that they have. So these are mainly the free versions, the open versions of the quantum devices that we can use. There are for some applications and for some maybe some for industrial applications, we could buy the use of those quantum computers by paying based on our requirements. So but today we will see, using these free devices, how we can simulate simple circuits and understand some of the interesting applications related to quantum computing. So if I'm to show you one of those quantum devices, this is IBM Oslo. And as you could see in this quantum devices, here, if you see, there is something called median C0 error and readout errors. So these quantum devices are not ideal. They have some error, and these errors would contribute to, like, if you are targeting an ideal, if we do an experiment and if you are targeting at an ideal result, it might interfere with these errors by the accumulation of these errors. So what quantum computing developing companies are trying is to minimize these errors and come up with better versions of them by different techniques. that you got some glimpse of in the previous session. So to go about what we can do with this IBM Quantum experience, we have shared with you a document where you will see how to create an account in an IBM Quantum experience, and then how to upload Jupyter notebooks onto it, and then how to configure your computer, your quantum, the quantum account, that you created to configure on running on quantum computers. So we will not go through how we are going to do it. Maybe you can, if you have not gone through it yet, you can just follow the steps and try to configure these things after the session. If you have installed, and if you have gone through this and tried to make an account, you can also try certain things that we have also shared the notebooks that we are going to use, so you can also run on your own and see how they work. So if you have not, it's okay, you can try it later on. So what we are targeting in this session is trying to understand some concepts and see that we can also implement them in quantum computers and debug them, and these tools might be helpful for us to understand the concepts as well. So we will start with the how to make the first circuit in Qiskit. I will name it as Hello World with Qiskit. So what we are going to make is the circuit that you saw in Kitman's last session, where he talked about entanglement. So here we will make this circuit, which will create a bell pair, and then we will measure it. So what we will basically do is we will create a Hadamard gate, and then we will create a control NOT gate, and then we will measure the circuits, and then we will run this circuit in a quantum simulator and see how it is. And then we will run this circuit in a real IBM quantum device and see what are the results, and then we could compare with our ideal one. So that's the plan that we are going to do in the first section of this evening session. So let me start with. So before starting with how to make the circuit that we're planning to, I will simply show you the main screen of IBM Quantum. So in IBM Quantum, you will see this when you go to the dashboard, you will see IBM Quantum Composer, which is the graphical tool that Kitman showed a little while ago. And then this IBM Quantum Lab is what we are going to use. And then this is the API token. If you have gone through the resources that we have shared, you will see at some point you have to configure your computer. This should be done at only once. So you can use this API token to configure that. So this will make you connected with those quantum devices. And that is the thing. And then I will show you how some of the, let's say, look at these compute resources. So when you look at compute resources, you can see the exact thing that I have put, I put as a screenshot in one of the slides. So you could see different quantum computers available. So your resources means these are the things that are available for you. In your thing, you will see some of those. And then you could see how many qubits are supported, like how many qubits, if you have a code, like when we are choosing a quantum when we are trying to see what kind of device that we would choose, we have to consider about this, the number of qubits that it supports, to see whether it supports the application's number of qubits. And then one other thing also, we have to look at the total pending jobs, which so you will have to be in a queue. So if you choose something like IBM Q2, so in that case, you will be getting somewhere like 68 in the queue, so it will take a while. So when if you want to choose something, like if you want to make it faster, or like if you want the results to be faster, you can try something with less number of jobs. So this is something you could look for to understand, to see the quantum devices. And if you go inside some quantum device, you could see this median C0 errors. And like when you're actually designing an application, you might be interested in what is the error. So you will have to look at those. And then these are the things that you could look for if you think of designing an actual application. And these things always change, like the values that might be there last week might not be the values that you will see in 1 week, because these things are moving so fast. So things are changing. So it is a good practice to see what the available resources when you are running a when you are trying to run something on quantum computer. First, now we will see how we are going to implement our first circuit. If you have any doubts or anything related to these things, you can ask on the go. So before starting our first circuit, is there anything that you felt unclear about? Okay, then we will move on to the first circuit. So I will not go through on all commands like one by one, but I will explain something special ones. You can definitely, we will give you some resources, specially shared by Qiskit, on how to program these things. Like it's basically using some commands, like you learn something when you learn Python, you will learn some of the commands, some of the libraries. So we will give you some resources to get hands-on with those. But here we will use some simple things and see with how we are going to implement the circuit that we mentioned earlier. So first, we like in anything else, like we will have to import some of the things to run this code. First, we will make a quantum circuit. So in this quantum circuit, we will have quantum registers, because we will have some qubits, and then we will have classical registers. If you remember, like once you measure a circuit, what you will have is a classical bit. So like to store those, we will have some classical registers. So first we will import those, and then we will initialize the quantum register. We want 2 qubits, so we will have 2 quantum registers, and then we will do 2 measurements, and then we will have 2 classical outputs. So we will have 2 classical registers, and then we will initialize the quantum circuit. So the quantum circuit will have 2 inputs into this function. So it would be the quantum registers and the classical registers. So in this IBM Quantum Labs, when we are using Qiskit, you can, if you want to see what the circuit is, you can just draw at any point. You can draw the circuit by using, if I name the circuit as Q circuit dot draw will give you the circuit, how it looks like. So so now when we see this circuit, you will see something like this. So this is the initialized circuit. And remember, in Qiskit, generally the quantum states are initialized to 0. So like if you want the state to be 0, you don't have to do anything, because because it is already initialized to 0. If you want to do initialize it to 1, you may be using XGate and like the not gate version of Quantum to transform it to 1. So now we will, in this one, we will see how we are going to apply the Hadamard gate. So for that, we can use the command qcircuit.h to denote the Hadamard gate, and then we will apply to which we have to say to which input that we are going to apply that. So it would be the first input. And then once you draw the circuit, you would see there's a Hadamard gate on the first cube. And next in our line, then now we know how to apply a Hadamard gate. And next we will see how to apply a control NOT gate. So these things, Hadamard gate, control NOTs, are mostly available in most of the in most of the applications that you will see today. So to apply a control NOT gate, it would be qcircuit.cx. And I will draw it for you. And once you draw it, it will be the C NOT gate. So a control NOT gate is something like you have to initialize what would be the target qubit and what would be the control qubit. So in this case, the QR0 was the control qubit and QR1 is the target qubit. So depending on the value of QR0, if it's 1, this operation would happen. That means it will flip the bit of the target qubit. And then to measure the qubit, there is this operation qcircuit.measure. So we will have to measure both the qubits. So we can measure QR and send it to CR. So we will have this circuit. So this is the circuit that we have made. Now, this circuit, you saw like how to initialize the circuit and how to do these operations, and then later on measure. Now we will go to the next step. So what is the next step? We are going to simulate this in this Qiskit simulator. So in this thing, first I would simulate it in a there are some libraries that you have to import, and then we will run this on a quantum simulator. So now here you could see in the back end, we are running a quantum simulator. So when we run it on an actual quantum device, you would see that we will change this part of the code. And then so it is taking a while. So once you run it on a simulator, once you initiate the simulator, you will have to execute the code. So to execute the code, you will have to send the quantum circuit that you prepared and the backend to be the simulator that we choose. And then after executing, we may want to find some results. Like now in this case, we are interested in the classical outputs of this. We are interested in what is there in C1. So in that case, we can use this after execution using this execute command. We can use the result dot result to get the whatever the results that it is getting. And to there is something going on here, like it's not completely running, but like you can try it. We can run it later on, but let's go through the document and then we will see what they are. And in this case, we will run it on the we have run it on a quantum simulator, but now do we know how to see process these data? So these are the things that you might be interested in to look at. So we will provide you some of the materials that you could look to identify what are the commands that now I have just used some only basic functions of the execution, which is result, and then I will only use something on quantum, like what are the classical outputs, but you might be interested in something more. So in those cases, you can use some advanced code, so you can learn them on the go from the references that we will provide. So and now we will have to see what are the outputs. So in any kind of language that you are like, any programming language that you are looking for, and then when you want to visualize, you have some tools. So in Qiskit also you have some visualizing tools, and you can plot histograms. And when you plot the histogram, you will get an output like this. So what does this output say is like, the code, they have run the code for 520 plus 504 times, and then in 520 times it has shown the output as 00, and the other time it would show as 11. So this is the output that you could see, and we will discuss why it is this. This is kind of an interesting observation, because it is when it is 0 at one qubit, the other qubit is also 0. So this is something you might, if you could remember that Kipling has started to show you with some cats that there are two kinds of cats, and then those two cats are of same kind in intersection. So this is some kind of quantum correlation, which is also related to entanglement. We will see how these are later on, but to begin with, now this would be our result from the quantum simulator. And next we will try to use it, try to run this code in a quantum, in a real quantum device. So in this case, we will have to use import IBMQ quantum experience and load our account. So when you load the account, you would see IBMQ as our account provider. So in some cases, you might be having different providers if you have bought some other devices. So in those kinds of things, you will have to find out what is the quantum provider. And in my case here, it is IBMQ. And then I will initialize the IBMQ as the provider. And then now we are at the point that we have to decide what is the backend quantum compute. So, but in this case, I have chosen IBM Oslo here. But when you are doing an application, as I mentioned earlier, you could look for what kind of thing that you would run, that you would choose depending on your application. And then similarly, as in the simulator, you will execute the code in this. And then you can also do something like monitoring the job. And once you monitor the job, you will see like what is happening in the job. So now when you do an execution in a real quantum device, your your job will be sent into a quantum device. And then when you run it, you will get something like job status. The job is queued at 30. So this means that your job is at the 13th place in the queue. So it may take a while to run the code. So in our case, I will show you something that I have run earlier on, so that it is taking. Okay, so this is something that is not run now, but it has been run earlier. So when you see the job result, you could see earlier in the real ideal quantum simulator, you only saw 0, 0, and 1, 1. But now you have 0, 1, and 1, 1, 0. So that means there are some quantum errors that are involved with some of the properties that is entitled with these quantum devices. So to reduce the errors, it is always helpful to look at what we can do with the quantum devices, what are their capabilities, to understand which quantum device to use. So now from this, what we want to make you aware is like there are quantum devices that you can run your quantum codes, and before quantum algorithms, before running those things on quantum algorithms, you can use a quantum simulator and then see what is the ideal response. And if it's the one that you're expecting, you can try to run it on a quantum actual quantum device and see what is the success of it. So in this case, we could see some errors, but still most of the things are inclined with what we expected initially with our quantum simulator. So this is the first application of Qiskit that you will see here. And so what we did was we created a quantum circuit like this and measured the outputs and see what were the outputs. So this is the task that we did. So if you have any doubts, or like if you have any other clarifications to be made, you can ask now if there is any, before we move on to some kind of application related to this, like using these quantum algorithms. So remember, like you will see this circuit again at some point in the presentation. So we will use this the things that we learn on the every step in some application and see how it goes. So if there's no other question, if there's any question, can go ahead. If not, we will. Now, what we saw earlier is like a quantum, running a quantum algorithm in a quantum simulator and a quantum device. But now we will talk about something like this word you might have heard from the earlier presentation, as well as when someone is talking about quantum things. Quantum speedups is like an interesting thing that people are looking forward to have. So we will look at some application which has a quantum speedup related to the classical version, but then this will be one of the simplest of that kind. But building up upon that, there are some interesting applications that have built on, and then that impact a lot in some interesting applications that I will show later on. So we will think about this kind of setting. You're given a black box algorithm or a function, and we are going to find whether that algorithm or function is satisfying a certain property. Let's say if you are given some kind of black box and you will be asked, is the output of this function is even, is the output of this function is odd, or something like that. So in those kinds of this is the setting that we are interested in, but we will consider more on Boolean settings, 0, 1, for this setting, for this case. So there exists an algorithm which is known as Josa algorithm. In that case, they are interested in, like, if you are given a function f, which is taking the inputs n Boolean inputs and sending out m Boolean outputs, and then we are going to find whether the function f is balanced or constant. So what balanced or constant means? Balanced is, so if you have 0 and 1, the number of ones and zeros in the outputs are equal. So here in this case, there's 1, 1 and there's 1, 0. So this is a balanced function. Constant function is, by the name itself, it would give one input, one output regardless of the input. So this is the task that we are looking at, whether to look at a function is balanced or constant. So if you think, like, you might be thinking why people would be interested in this kind of application. Yes, it might not be the most interesting application, but you will see some kind of quantum speedups, and this is kind of a foundational point in building up something interesting. So if I ask, if we think of classically, and if we set up this to something of, let's focus on something like n to be 1 and m to be 1. That means we are considering about a function which takes one bit as the input and one bit as and the output is 1 bit. So in that case, we will see how many times that we have to access this function to determine whether the function is balanced or constant. So for instance, if you are given this function, the balance function 1, 0, to determine whether this is balanced or not, how many times that you have to access this function? Anyone has any idea about it? It's like the classical setting. You are given an algorithm, you are given this f function, and then you have to identify whether it's balanced or constant. So you just have one input, one bit as the input and one bit as the output. So how many times that we have to use the function, like you have how many times that you have to put an input to the function and get the output to see whether it's balanced or constant? Are there any guesses? Yeah. So there is one answer to yes. We need 2 times, because once, if you consider one input as 0, we might get 1 as the output, but we don't know what will be the output if we input 1. It could be 1. If it is 1, it will be a constant function. If it's 0, it's a balanced function. So in classically, we may need 2 functions. You have to access the function 2 times. But what I'm going to claim here is that a quantum computer needs only 1 query. So this is what we are going to see. So this is related to 2. Now we need 1. So it is not a huge amount to see the improvement, but still it's an improvement. So if you are given, let's say, a function of 2 inputs, so then I would say that for a classical computer, you need 3 queries to understand that. Why do we need 3 queries? It is because, like, if we check 2 inputs, let's say if we check these 2 inputs, if we check these 2 inputs and we get the output 1, 1, but still there's a chance that these outputs could be 0, 0. So then we would say it is it could be a balanced function. But if we try 3, we will see if it is 1, then it can't be a balanced function. And like here we assume that in this case, the functions are either balanced or either constant. So in that case, we need 3 queries. But our claim is that quantum computer needs only 1 query. So you could see when the input to the function increases, you would see more improvement in what kind of what a quantum computer could do. So for what we are trying to do in this session is trying to justify this claim, and then we will validate our claim using a Qiskit application. So our setup is related to this. So we will have 2 inputs and 2 outputs. And if you have, we have 1 bit, so there are 2 options, 0, 1, and one output bit which has 2 options, 0 and 1. So if you think of how many such functions exist, there are 4 functions. What are they? It would be all mapping to 0. all map into 1, and all would be identity. If it's 0, it would be 0. If it's 1, it's 1. And 0, 1 would be, sorry, this should be 1, 0. So this is the negation. So, and now we will see, like, if we are going to think of these things, we have to know how to implement these functions in a quantum computer. Now, in a classical one, we can just input the input to the function and get the output. But here we are thinking of implementing functions in quantum computers. So we have to be careful of certain properties. So the quantum circuits that we want to implement should be unitary and reversible. If you could remember that Kitmin was mentioning about reversible is a major need, it's necessary in quantum circuits. So if you could remember the X gate, once you apply the X gate and then apply the X gate again, you can take, if you had the output 0 here it would be 1, and here it would be. So this is reversible. You can get what it was earlier back. So once we are implementing a function, we also have to think of that. So if we just put a function like as we did in classical thing, like if we have x and if we output as fx, will it be reversible? Like if it's reversible, how it is, and like if it is not reversible, are there any kind of count examples that you can think of? You can think of the 4 possibilities that we saw earlier, and if there are any guesses on like whether it's reversible or not, or like if it's reversible how, and if it's not reversible, what would be the count example? So if you could recall here, if you look at this function, if the function inside the black box algorithm was this, then both the outputs are 0, 0. So once we have 0, 0 out there, you don't know whether the input is 0 and 1. So it is not a reversible function. If we use this, it is not reversible. So this, if we try to implement this like the simplest way, it would not be reversible. But what if we do like this? We will take some extra qubit. In earlier, we were having only 1 qubit as the input, but we will get 1 ancillary, like supportive qubit. And then we will do this function. What does this function does is, if we taking the inputs to this function as x, y, it would turn the thing to x plus y XOR fx. So this is the XOR function. So XOR operator. So what it would do is, like, we have x and y qubits, and then you do the operation on it, and then you will have x and y XOR fx. So this, we have used some ancillary qubit, like the supportive qubit, to make it reversible. So this is, yes, is this reversible? Yes. But how? How are we going to show that this is reversible? One way is like, as you could do in when you were doing X gate, and to show it was reversible, you applied X gate on X and again X, and you could see the inputs and the output was same. So if you do the same technique to here and see whether that works here. Let's try whether we are trying to see whether this is true. So what we will get if we apply once this function, it would be x and then y XOR fx. And now the inputs to this unitary function would be these. So what it will do is it will keep the first qubit as it is. And the next one, it will take the input and add fx into it. This addition is XOR. So now you could see you can use these properties. So once fx XOR with fx, it would be 0 by 0, and this is equal to y. So indeed it is reversible. If you input xy, you would see the output as this. So this is a reversible function. So this is kind of a technique that people use in standard ways when you want to implement a function that we know in a quantum computer to make it reversible. So this is something that not inherently for this application that we are using, but if you are to implement some function in a quantum computer, this might be the standard way, or else like one way that most of the people are using. There might be some interest in other ways that you could think of, but for this is kind of the standard way. So now we know that this is a reversible function. So now we will do some example. So if we are to if we have the function 0, 1 mapping to 0, 0, what would be the how are we going to implement the unitary function? So what we want here is like we want x to be x and 0 to be 0. So the output, we want the output to be 0. So this can be achieved if this is like the identity. So you don't have to do any circuit. You can just use Q0 and Q1. And if you are to apply Oracle for the constant 1 function, that means you want to make the function 1. So what we have to do is, earlier we were having this as 0. So if you want to change it to 1, you will have to apply an X gate. So that's what we are doing here. So in the balance function, we want 0 to be mapped into 0 and 1 to be mapped into 1. So so what we want is, what we want is 0 to map to 0. So it's 0. So let's take the input to be 0 here. If we have 0 here, 0 here, the output would be, this is the control not. So once the controlled is 0, it will not change anything. So when it is 0, the output would be, when it is 0, the output would be, now we are inputting this, and the output would be 0 here and 0 here. So that's what we want. When the input is 1, let's change this to 1. Then this control NOT gate is activated. So then 1, 0, now this X will activate and it will change 0 to 1. So you could see it is X here, X here. So this is one way that we could implement this function in a quantum oracle, like if we want to implement as a quantum circuit. And then if we are to do it the other way, the reverse, the inverse of it. So what we have to do is, like, if earlier it was, the output here was 0, 1, and if you want to invert it, you can apply X gate. So this is simply, these are the ways that we could make those functions. So this is the summary of how these functions can be implemented as a quantum circuit. So this is an interesting thing that you could think of when you are even doing something related to any other application. You might be implementing a function in a quantum computer, might be one of the basic things that you might have to do when you do some customized application. So this might be the thing that you could try at the first way when we are implementing the algorithms. So are there any questions? Okay. So now we were looking at how to implement this unitary function. But what we are interested in this specific application is like you are given this unitary function. Once you are given this unitary function, how are you going to decide whether that function is a constant function or a balanced function? So what I claim is if you implement this circuit, and if you after you measure, if you get the output here to be 0, it means this function is a constant function. If Z is equal to 1, it would be a balanced function. This is what I claim. And like, if you want in like this, things can be easily verified with mathematics. Like if you can think of what is the state at this point, what is the state at this point, what is the state at this point, and likewise you can go forward. But like in this workshop, we are trying to make you familiar with the concept. So we are going to run this on a quantum with Qiskit, and then show you that indeed this is how it works. So we will put some function that we know whether it's constant or balanced, and then we will show you that we indeed get these kinds of observations when we run it on an ideal quantum computer. So that validate in this quantum circuit. So now we will go back to the implementation, and then we will implement this quantum circuit. And this is in your resource folder as demo dos Josha. So you can look back on this again after the session as well. So we are going to implement this circuit. So now you know like disk, edge, X, edge, and those things are simple single qubits that you could implement like we did in the first example. And this oracle also you can implement from the oracle for different functions. We looked at how to implement the oracle. So we will use those oracles, and then we will implement another Hadamard gate and then measure it and see what is the output. So now we will go back again, and then to the Qiskit notebook. So now you can, so we will consider the George-Joseph algorithm. And like, I will not go through most the initialization phases, but you will have a import, like you will have to import this all the things that needed. And then we will also implement the oracles that we mentioned. So first it will be the oracle that we give 0 as the output always. So it would be this. And then we will do it for the oracle which gives 1 as the output always. So it would be this one. And then the next oracle which gives the same as the input as the output. And then the next oracle will flip the thing. So like the first two ones are constant oracles, while the last two are balanced oracles. So we can choose one of the 4 possible oracles to understand whether like we can try all 4, but for here, like I choose the let's say I choose the first constant oracle, second constant oracle, which has all 1. So if I have this, and then you can look at how this is implemented, but this is also basically the same ways that we have looked at in the first circuit that we looked in the beginning of the session. I will not go through most of the codes part, but let's look at the circuit. So now we implemented this circuit. So what we did, is like we implemented this part of the circuit, and this is the UF function that if you could see my cursor, this is the one between this is the UF function, and then we apply the Hadamard gate, and then we measure it. And then after measuring, so what we are now, we have given a constant function into it, and now we are seeing what is the output. So we have seen the output when you measure this qubit, it is always 0. So it is valid, at least validating for this scenario that it is 0. You can try for other cases and verify that it indeed satisfies what we claimed. Now, this is related to this input, when taking the function with the input of 1 qubit. What if now next I will use what Qiskit has implemented using they have some improved codes that you could just change in the number of qubits, and then you could get the circuit. But so I will not go through all the circuit, but we will see the circuit, and it is a direct in thing. Like if you see, it is the same circuit like you saw earlier. We have 1 qubit more. If as with the inputs are now twice, so you will have what you did for 1 qubit, you will do it for the other qubit as well, and then measure both the qubits. And if both the qubits are 0, or if both the qubits are 1, it is a balance function. So in this case, we have input a balance function. Once you have input a balance functions, the output of this, both these qubits should be 1, 1. So if it was a constant function, it would be 0, 0. So now we will run it in a quantum simulator. So once we run it, we will get the output as here 1, 1. So as we expected. This is all based on ideal quantum devices, not anything beyond that. So what if now we are trying to run it on a real quantum device? So in this case, also I have run it earlier, but if you, it will take a while to run it. And then here we have used something called, there are some things that you don't have to manually look and see, look whether which is the busiest or which is the least busy one. There are some commands that you could use the least busy one and then try to use that quantum computer. And then in that case, I have run it on a quantum computer, and what you got as the output is this thing. So we were expecting 1, 1 for everything, but what you got as output is 0, 0, 0, 1, 1. You have got something. So there is a chance that it would go wrong. So that is the errors that nowadays available quantum computers are having. So what they are targeting is improving those things so that these errors are minimal. Now, if we do this same thing for a constant function, you will get something on 0, 0 instead of 1, 1. And then if you run it on the same way on a quantum computer, you will see this, like we were expecting 0, 0, but you were getting 0, 1 and 1, 0. So there you could see something interesting. You didn't get something like 1, 1. So this could be something related to that quantum computer where it has more error to turn 1 to a 0, rather than when turning to a 0 to a 1, the error might be less. So these kinds of things are kind of, you could think of those things as like when somebody is designing a quantum computer and doing experiments, these might be things that they are thinking of, because this, like, there's a higher error of in this experiment. We can either claim like it might not be the exact reason, but there might be we can guess like there's an error of making there's a higher error of making 1 to a 0 rather than 0 to 1. So it might be different in another quantum device. So it is an interesting observation of what are the things that we really could do in quantum now, but in the future we don't know. The things are more promising, so things might go in the way that we expect as well. So if you want, you can go through the mathematics of this deriving these circuits and verify these like things, but we try to verify that using a quantum like a Qiskit program. Like you could play with this and see whether it works, or like you can compare the results and see how it goes. So now let's go back to our So we implemented this circuit and then we verified this claim. If we want, if the function is constant, we can, if we said is 0, it is a constant function. If it is 1, it's a balanced function. If when the inputs are increasing, we were thinking of if there were 2 qubits, two inputs other than that, we wanted something like if we had he said 1 and he said 2, we wanted both of them to be 0 to be a constant function. And if both of them to be 1 to be a balanced function. So these kinds of things we saw from our Qiskit application, but if you're interested, this is basically just applying some linear algebra tools, and just this is not a very hard job of finding what the outputs of this circuit at each point, and then try to verify it as well. But to get the gist out of it, like so what we wanted to claim initially was like we need only one quantum. We use this UF only once to figure out whether it's a constant function or a balanced function. And then we implemented that in Qiskit. So now we will look at, like, this is a quantum speed up. As you saw in the 1-bit functions, it was like classically we need the 2, but now in quantum we need only 1. And if it was 2-bit function, and then classically we need 3, but in quantum still we need 1. So if you think of this then in more general n-bit functions, classically we might need 2n-1 plus 1 queries to the oracle in the worst case. So it's like you will have to try at least half of the things. So it would be 2n divided by 2, and then we have to try at least 1 more than that to verify it's a balanced or a constant function in a worst case. So in quantum, it's only 1 query. So when n gets larger, the speed up, like the improvement is huge. So this is what George-Joseph algorithm, the speed up is George-Joseph algorithms speed up is going to be. But still, people could claim this is not an interesting application to begin with. But all this, there are some advanced algorithms to identify interesting properties, like a period of a function. So in that period, which is also known as Simon's algorithm, and then factoring algorithm is also of similar format, using something called quantum Fourier transform along with these similar kind of settings, and that this is known to be as Shor's algorithm. It was implemented in like 1994, which made a huge change in the perspective of quantum and what quantum is capable of. Because if we find out the factors of a, if you are given a number and if we could find a factor of an algorithm with exponentially less time, it is enabling us to break down RSA encryption. So if you are familiar with some cryptographic settings, in cryptography, we think of, like, we assume that there are computational restrictions, like you will not have or will always have bounded computational resources. So in that case, in classical world, you might not be able to find out the factor of an algorithm. Given a number, you might not be able to find out the factors. But if a quantum computer is there, then you can find it with exponentially less time, and that would break the RSA encryption. For instance, you are doing a transaction with a bank and you are getting that OTP to your phone, and then during that time, if a quantum device could find out this OTP by factoring, like this factoring is one of the basic ingredient in this RSA encryption procedure. So then if you could find it, and then somebody would hack into your account and do whatever the transactions that they want. So this is scary. So this motivated, this is one of the motivations in the booming of quantum field in general as well. So these are kind of quantum speedups that you could achieve. And then these are kind of, so you could see that a quantum computer can bring out threats to classical models. Then you might have to look what could be done better to avoid those threats. And then this is how this designing processes are going on. So like once people saw this, there's a problem with cryptography. In cryptography, there are some problems when it comes to quantum, and then they kind of looked for what post-quantum cryptography, what would be after quantum, what would be the cryptography notions would be. So people are looking at those kinds of things because of this kind of Shor's algorithm brought a whole new field of research in cryptography as well. So this is kind of one part of what I was planning to discuss. So are there any doubts or clarifications that you want me to do? You can go ahead. Like you can ask any doubts, because like when I was first learning as well, I had a lot of doubts, and but it takes a while to understand some of these things. Like I also still learn some of these things. So you can ask those questions. Okay. Now, earlier we were looking at some of the quantum speedups. Now we will look at what kind of quantum properties, like some things which were not there in classical world, but because of the quantum in the quantum world, these properties may be advantages in some sense or disadvantages, or else like we have to be careful when designing our experiments. First thing is no cloning theorem. What it is like in classical data, if you want to copy the data, you can just copy it in some hard drive or something, or else you can write it down, or like you can duplicate it by photocopying or something like that. Classical data can be copied and duplicated, but the quantum states can't be copied or duplicated. So this means, like, if you want to do some kind of copy and duplicating task, like let's say if you were trying to do some statistical task, like earlier you could generate data and then copy those into some something and then use it again and again to try out some things. But here, once you make constant quantum state and you can't copy it, so if you want to make that use that quantum state, you will have to prepare it again. And then it would be a new state with the same properties. So this is the no-cloning theorem. At a glance, you might be seeing that it is disadvantages, but there are because of the no-cloning theorem, there are some some interesting security applications which are known to be as quantum cryptography. They use this no-cloning theorem is very helpful in certain settings, so to ensure security. So this has advantages as well as disadvantages. But this all depend on the application that we are interested in. And the next property, this is something that you have seen in the first session as well, as some of the measurement postulate that you would use. So here, when we have a quantum state, once we apply the measurement, original state may collapse. So what it means is, like, for an example, let's say we have a state which is in superposition of 0 and 1. So if we do a measurement on Z basis, so that means, like, if you do a measurement to figure out it is 0 or 1, then you will get 0 with probability alpha squared, like absolute value alpha squared, and you will get 1 with the probability absolute value beta squared. So this means, like, once you do a measurement, you will not have the same state that that you were earlier having. So, but remember, it's like if you initially had 0, still doing a measurement will definitely give you 0. If you have 1, if you measure it again, it would be 1. So, like, it will collapse if it was in a superposition, which is the interesting case here. So it would the superposition, where if it's in a superposition, it will collapse to some other state, and then once we go to that state, we can't recover the earlier state. So these kinds of things are some things that we have to be careful when deciding quantum algorithms. When we are measuring, we have to be careful that once we measured, we will lose most of the information. So we have to be careful at what point that we should do the measurement. So that is one of the things that, like, these two properties are kind of interesting in their own, and these things are the things that we have to be careful when designing algorithms. So next, we will try to use, like, now we have seen this, we have implemented the first circuit in Qiskit, and then we saw some of the quantum speedups, and now we have seen quantum properties involved. Next, we will look at something called quantum teleportation. You might not have heard of quantum teleportation, but you might have heard of teleportation. So this teleportation, at least in science fictions, you might have heard, like, you want to change, you will dismantle, like, let's say we have an object and we have a person, we will dismantle that person and reassemble that person in somewhere else. So this is then that person is teleported from the first location to the other location. So is it actually possible? At least in science fiction, yes, but in reality, is it possible? So this is kind of a philosophical kind of question that people have been talking about. So then if it's possible, we will be having a question of, like, once you dismantled and rearrange that, it's somewhere else, is it exact you that has been teleported, or else someone else? So, like, who is the real person? So these kinds of philosophical questions come up. But as far as I know, the quantum teleportation is the one that experimentally verified. Because of these experimental efforts, the Nobel Prize owners, like, for this 2022 they were contributing heavily on these kinds of experiments, on realizing quantum teleportation, in real world networks, and making all these experiments, designing those experiments and making them work. So to see what quantum teleportation is, like it's also having the flavor of transport. Like we have a state with somebody and we want to send it to someone who is very far away, or like maybe in two universes or something like that. So then what in quantum teleportation is, what we are looking at is, we have a quantum state. Let's say Alice owns a quantum state, and then he wants to teleport that to Bob, and then how he is going to do that. So in this case, we have to be careful that we are not, here the teleportation happens of quantum information. So what we want to send is the quantum information of that state, and and at the Bob's end, we will get those quantum information, and then it will help us to recreate that state in Bob. So then when you are transmitting that state, when these things happen, the Alice will lost the state. So how it, like, as we have seen from no cloning theorem, quantum states can't be copied or duplicated. So if it was not like that, you could have copied it into somewhere and then send it off, and then Bob could copy it from that. But it is not possible. But if not, Alice could look at the state, and then look at, in the sense that he will have to do some measurements, and then, but once Alice is doing measurements, it will destroy the superposition, as we saw in destructiveness of measurements. So then he will not have an idea of Alice saying something about the state information to Bob. But one way would be, like, let's say if Alice has multiple number of copies of the state, so then he would do some kind of statistical test and would say some information to Bob about the quantum state, but it will not be giving the entire information of the quantum state. But we will see that there is a mechanism that one could look for to see that quantum teleportation is possible using the interesting properties of quantum, like quantum entanglement, that you have heard in the previous sessions. So these kinds of things will be helpful for us to achieve quantum teleportation. So how it works, before looking at how it works, now, as I mentioned, the first circuit that we made is of importance. So let's look at that first circuit that we made. So in this case, if we think of the output state of this circuit, it would be of this format. So this is an entangled state, because like we didn't cover much of the mathematical side of it. So an entangled state generally can't be written as a product of two states. So in this case, it can't be written as product of two states. But here, you could see there is some correlation. As I mentioned in the when we were doing the first circuit, there were some relations. When you measure one qubit here, if we see 0 here, then the other qubit is also 0. So these kinds of quantum correlations happen. So this is the entanglement that occurs. So this is what we saw as correlations. So this is related to quantum entanglement. So we will use this circuit to achieve quantum teleportation. When Kitmin was doing his second session on things, he showed something related to Bell states. So what we prepared earlier here is a Bell state. So this Bell state could be represented in this format, and Bell states are entangled state. And we saw how to create this Bell state that we have learned in our the first circuit. And now we will see something called Bell measurement. So what does the Bell measurement do is it will entangle first by the C node, it will entangle these qubits, and then we will add a Hadamard gate, and then we will measure these 2 qubits. So this kind of measurement is known as a Bell measurement. So you might be wondering why this is Bell state, Bell measurement. So there was this researcher back in time, John Bell, and he was looking at these things in like at least in theoretical sense, like he verified things like Bell inequalities, some things that we will not discuss here, but he was pioneered in finding out some kind of theoretical verifications of certain things, but these things were actually not, he could not verify them practically, like practically he could not, but the Nobel Prize owner, winners for this year, for the last year, was capable of doing those things after Bell. So this is why these things are known as Bell states, Bell measurements. And you could see most of these are very of the same nature, where like there's a C node and there's a Hadamard gate. So what it does is doing entanglement and doing some Hadamard gates to have some kind of superpositions. So it's the same way that it works. So now we will see how we are going to achieve the quantum teleportation. First, I will give you some steps and then I will illustrate how it is. First, Alice has 1 qubit with state psi. Let's say it is the state that we want to teleport. And then Alice and Bob share an entangled state, which is like the Bell pair that we are going to use. Bell state or Bell pair. And Alice apply a Bell measurement, the measurement that we saw earlier, to his 2 qubits. And then Alice send the outcomes of these measurements to Bob through a classical channel. Then Bob does the correction circuit. Now Bob has the circuit, has the state psi. So this is the basic steps related to quantum teleportation. So it's not very complex, but it is involving this Bell state and a Bell measurement, and then doing some classical, some measurements, and then transmitting them through a classical channel. So if you look at this, so what we do is like first, this Alice has some state, and then it make during that time, Bob and Alice share some quantum entangled state, Bell state. So this Bell state, in like, if you think of how it is, even somebody outside could make a Bell state and give one end of it to Alice and one end of it to Bob, or else someone, maybe Alice makes that state, entangled state, and send one of the other qubit, the other end of the qubit to Bob. So there are different ways of achieving this. For this here, let's say we have a Bell state, like entangled state shared between Alice and Bob. And then what does Alice do is Alice will do a Bell measurement to his own qubits, like the one pair of the entangled state and the state that he wants to teleport. And here, once he does the Bell measurement, he will lose most of the information about the state psi. So it is destroyed, the state psi is destroyed at the point of Bell measurement. And then once the Bell measurement is done, but still Bob is not able to find out what the state. For this to be successful, Alice has to send what were the outcomes of the Bell measurement using a classical channel. If this classical channel was not available, then Bob can't achieve the to get the teleported state. And then based on these classical outcomes, Bob will do some correction, and then after that only he will get the state psi. But once he get this state psi, Bob will not have it. So this protocols destroy the quantum state in one location. Here it's in the location of Alice, and recreates at a distant location in Bob. So this is the quantum teleportation protocol. So before moving on to like the circuit itself is like making blocks. Like now we know how to make a bell pair, and then we know what is bell measurement, and then we will combine those circuits together. And then for this modification, we will do some extra circuit part, and then it is the quantum teleportation. So it's like 3 building blocks would create one of the fascinating applications of quantum, which is quantum teleportation. So these kinds of quantum teleportation is an interesting thing in terms of when somebody is thinking of quantum networks in general, like quantum communication. This quantum teleportation plays a huge role because it is helping to transmit some quantum information from one end to the other, which is like the major requirement in a network. The communication is a major requirement. So that's the protocol. And now we will combine the circuits that we now here. This one would create the bell state, and this then would do the bell measurement. And then we will transmit the classical, what are the outcomes to here. And then depending on the outcome of, we will activate X. That means if it's 1, we will activate this X. And if this has outcome 1, we will activate this. So this is this correction, like we will show next, like this correction is indeed necessary, like for the completion of quantum teleportation. So this is like, you have seen these building blocks now in the previous session. So what we have done is combine those together and see and look at the quantum circuit. So now we will see what is Bob's correction. If you do the maths behind this, you would find out like, now you can believe me for the time's sake, like if you have the measurement outcome 0, 0, whatever the Bob's qubit would be this thing. So it is the exact qubit. But if it's 0, 1, then it would be something different. And 1, 0, it would be another thing. 1, 1, it's so this in teleportation, they have these things like, if you want to instantaneously change the state, like teleport something to another, so to somewhere else. So this instantaneous fact will not work, because here, to identify the state, we have to send these measurement outcomes to Alice. So to send those, we have to use a classical network, like maybe a standard, like a classical internet, maybe a classical channels, any kind of classical channel. So this is adhering to speed of light. So you can't do anything faster than speed of light, but you will do it either in the speed of light or slower. So and then, because if you don't know these things, all these states are equal probable, and then it's not Bob can't find the state correctly. So we will see what the correction of this. Now for this alpha 0 plus beta 1, this is the exact state that we wanted to transmit. So for 0 and 0, we don't have to do any correction. So that we can achieve without applying X and Z. But let's say we want to correct 0, 1. What should we do? Now you could see these operators and what they are doing. Like if you could remember what Kidman was graphically illustrating you, what these X gate, Z gates are doing. So this depending on these things, can anyone guess what we should apply to this out? If we have measurement outcome 0, 1, what is the gate that we should apply to turn it to the exact state, this one? Now, we have this state, but we want to make it to this state. What should we do? What could be the operation that we can do to turn this into the state side? Are there any guesses? So, okay, let me see, like, if you could see here, now here, if we want to change this to this state, what we want is to change 1 to 0 and 0 to 1. So what kind of gate it would change this alpha 1 plus beta 0 to alpha 0 plus beta 1. So it would be like we want to change 0 to 1 and 1 to 0. This is done by the X gate. X gate is if we think of the classical analogy, it would be the NOT gate. So like 0 will be mapped to 1 and 1 would be mapped to 0. So if we apply X gate, you would get the state psi. Likewise, if we try to do it for 1, 0, then now what we want is we want to change 0. We want to keep 0 to 0 and 1 to be minus 1. So this minus is a phase factor that when Kitmin was simulating that, you could see that the phase factor was changing directions as well. So it would have minus factors when it is phi, when it is a phase difference of phi. So this can be achieved. If you see here, it would be achieved if you apply Z gate. And for 1, 1, it would be interesting to see this in 2 steps. We can first try to make it to alpha 0 minus beta 1, which can be done by the X operator because we just changed 1 to 0 and 0 to 1. And now we have this state. Once we have this state, we can apply Z like we did here. So we will have to apply X first, Z next. Then we can correct this. So this corrections, what I want to highlight here is like without the measurement outcomes of values, we can't achieve the quantum teleportation at the end of Bob. So it will not violate the speed of light. It can't be done instantaneously. It is necessary to have these measurement outcomes to find this correct state, to like get the correct state at Bob. So now, so far we have looked at this, like I have verified, like I have told you what the circuit is and like how it looked like. So what we are going to do now is like we are going to implement this quantum teleportation circuit with Qiskit and see how it works. So like you can find this demo in quantum teleportation in the resources GitHub site. So then you can try it on your own as well. And now we will look at that. So you could see here the things that we have looked at is there. So we were creating a Bell state here, and then we did a Bell measurement. If you think of this whole thing together, you will have a Bell measurement, and then you will transport through a classical channel what are the outcomes, and then depending on those outcomes, X and Z would be X and Z would be operated based on whether it's 1 or 0. Well, if it's 1, it would be operated, and then you will get the state psi. So now we will see in a Qiskit application how this is like. Indeed, this happens. So we are going to verify, like we will not do the maths of it, but we will verify it through this Qiskit simulation. If you have any doubts, you can ask in meanwhile as well. So this simulation is mostly based on Qiskit's quantum teleportation one. Like first, we have to do the necessary imports, and then we have to set up the circuits. Now, I will not go through each and every circuit because we have looked at how to make our first circuit. And then like there are some additional things that we could do, like we can name the qubits like with whatever we want. So there are some kind of arguments that we could put into those functions to make it cool, like to make it presentable. And then we will create a bell pair. And once we have the bell pair, so we will first create a bell pair. This is what we wanted to do initially. We want to make the two qubits entangled. So this, you have to remember that here Q2 is with Bob, Q1 is with Alice, and Q0 is with Alice. And then we would do some, Alice would do some gate operations. So what Alice would do is he will take his qubits, Q0 and Q1, and then he will do the bell measurement. To do the bell measurement, he will first apply the C naught and to make it entangled, and then the Hadamard along with making it entangled, and then afterwards it will measure the output. So now we have done the bell pair and the bell measurement. Once we have done that, we will apply the correction gate. So if we have inputs 1 here, if we have got the outcomes 1, we will activate the X and Z gates accordingly, and then we will make this circuit as it is. So you can run these commands and then obtain this. So now what we are going to do here is first, now how to verify that. So like we can't measure at, like we can measure at this end of the state. We can't measure and then say, because when we are measuring, we will not see the exact state. But there's a clever way of, like, we will first create a random state vector at Q naught. Like at Q naught, we will try to make a random state vector, and then let's say psi. So if we create the random state vector, it would be, so here I have randomly selected a state vector. You can use, like Qiskit has necessary inputs that you could make, create a random state vector. And then, so what we have got is a state of this kind. So this is what we are going to teleport now. So given this state, psi, we are going to teleport it. So what we will do is, like, we will apply the circuit that we designed. And now here, this is the, so this part is the, if you could see the cursor, this part is the circuit that we designed, and I input the state that we initialized as our state vector. After doing that, all these things, I will observe, this is what we could do with a simulator, because like we can't measure them. So here we are trying to see the state vector. So we are trying to save the state vectors at the end of the at the end of these operations. Once these corrections are done, once these things are done, we can try to make it see what is the state. So now when we implemented these things and see the output of each qubit, you could see the first qubit has turned to 1, and the second qubit has also turned to 1. And then the output state has turned to be this. So if you could let me remind you what was the original state. So this was the original state, and now you have also got the original state to the qubit 2. The qubit 2 is owned by Bob, but you could see now Alice doesn't have any information regarding this state psi with him. So his states are 1, 1. Like the other possibilities would be it could go for 0, 1, 0, 0, and or else 1, 0, those kinds of possibilities, but it will not have information about psi. So this shows that it has destroyed the information of psi from Alice and given Bob these things, so the quantum information. So this is basically quantum teleportation. So this is like you can try with different state vectors and see this indeed satisfies. So this is one kind of illustration. Are there any questions? Okay, if you see here, I just used a simulator to do this. What if we are going to use a quantum computer? So I will not discuss that part here, but when you are doing a quantum computer, how we are going to do this transport, like we have to transmit the classical information. So how are we going to do that? So then in these kinds of settings, people are looking at some interesting ways of like connecting these circuits with some kind of controlled Z gates, control X gates, and doing the measurements at the end. So these kinds of interesting possibilities are there if you are going to simulate this in a real quantum device. So these kinds of things you can dig into now with having the this simulation that we have run on a quantum simulator, and then you can try to do those kinds of operations that we will provide you with the references of Qiskit, which you can look through to figure out how you can do it with a quantum computer in a like how to make this scheme work in a quantum computer. So now we implemented this quantum teleportation circuit with using Qiskit, and then we saw that we could transmit, like if we had a state psi here, we could teleport it to here with say state psi. So now if somebody is thinking about teleportation in general, like is in some kind of philosophical questions, like is it the same you once you have teleported from one location to here? At least in quantum teleportation, it's not the same one. You destroy the things here and you remake it somewhere else with like the same property. So it's like it is learning the quantum information there and recreating the quantum information out there, rather than taking the exact exact materials or molecules. Like let's say the state psi is made of some kind of molecules. Like we are not saying that exact those molecules have gone to Bob, but what we say is the arrangement of those molecules, the state is the same, is transferred to Bob by this quantum teleportation. So there are like limitations on like what is capable to do and what is not. So these things may give you some hints on those. Next, we will use quantum teleportation to do something more. This is also something that has been verified by experimental physicists over the past years. So in this one, they are using teleportation to make some entanglement of states which are not physically together, or else they will not directly interact, but at the end of these operations, there will be an entanglement between some other states, some other individuals. So this is something very important in the case of, if we are trying to look at quantum networks, this would be something interesting to look at. So this is the setting. Let's say Alice and Bob has a bell pair. And then Alice and Charlie also have a bell pair. And Charlie and Diane is also having a bell pair. But Bob and Diane are not interacted directly. But what they will do, first, Alice, a teleportation would happen between Alice to Bob. And next, teleportation would happen between Charlie to Diane. So these two operations, like if you think of quantum teleportation, like once you do the teleportation from Alice to Bob, it would get a state of this state to here to Bob. And then when Charlie and Diane is doing the quantum teleportation, it would get the state of this, the other qubit in the Charlie's end to Diane, and then they will be in entanglement. But now this is without any interaction between Bob and Diane. Bob and Diane will get a bell pair, will share a bell pair because of this teleportation. So this teleportation is a key for many things. So entanglement swapping is like one of the other interesting like advancements, which is clear, which becomes true through quantum teleportation. Are there any questions? Okay. But now when you look at teleportation in general, quantum teleportation in general, we assumed a bell state to be between this Alice and Bob. And then these kinds of things are like, we are exactly wanting the maximal, this is something related to maximal entanglement. So they wanted the states to be maximally entangled, even though we didn't discuss this much. We wanted those two parties to be maximally entangled. But what if it's not perfect, like not maximally entangled? So these kinds of, it might be hard to make those circuits in reality. So there will be something like not perfect quantum teleportation. There are some interesting research directions that people have looked at, not trying to do something related to probabilistic teleportation. So it's like with some probability it comes true, with some probability it might not, it might go wrong. So these kinds of things, and then to make that high probability to make it work. So these kinds of things are like research directions that have been that have been done on top of teleportation. Like there are different versions of teleportation, like with different things. Like now here we transmitted 2 bits of information. People are also looking at things like, what if we reduce the entanglement, but like we reduce the amount of entanglement, like not maximally entangled, but what if we increase the classical information? Can we do better? Those kinds of questions are like people are trying to understand because of because we don't have these ideal quantum devices. So for these things to actually try to make it work in a big scalable sense, it might be important to look at those kinds of settings as well. So this is a glimpse of what is possible. So there are different extensions. If you are interested, you can, like, based on what you have seen today, you can look through some kind of interesting generalizations, interesting applications on top of quantum teleportation. So I think we have looked at now most of the things that I was planning to discuss. If you have any questions, we can look back again. Are there any messages in chat? I think no. Okay. First, we looked at Qiskit and IBM Quantum Experience, and like we saw like how we can use the IBM Quantum Experience. So it's like we use here Qiskit and IBM, but it's worth to mention that as we showed you, there are different other tools as well. So if you are interested, you can look through this. But I would say like you can look on one thing and learn the concepts, and then I think in most of the platforms it would be similar, only maybe the syntax changes a little bit, but if you understand the concepts, it would be you can play with any of those tools, but these tools would be helpful for us to understand things better, and also like as Kitman mentioned about the quantum journey, like quantum once we want to do something, we have to do like a lot of things to get the measurement outcomes out. But in with these kinds of things, we were given the chance to do something on like a Python notebook, and then we will do we will just send some jobs to the quantum computer, and everything is like they have made all the infrastructure for those to work. So this is a nice thing to try out the quantum circuits. And then we looked at some kind of quantum speedups, like motivate you on what kind of speedups that we could achieve. And then we looked at quantum correlations and how entanglement helps. And then at the end, we talked about quantum teleportation. So, and to note you that everything that we discussed in this whole workshop, maybe it's more of not, we are assuming that there is no noise in this, so noiseless case, but when noise comes, we will have to do something different in understanding how these things work. So there are some kind of things related to challenges. So if you have any questions, we can go for it. If not, we can look at what are the challenges that we might, and we have already seen them throughout all these discussions. You might have heard, okay, there are limitations. We can do this, but there are limitations. So in anything that we do, there are pros and cons. So it's always good when you have something, when you learn something new, to learn what is possible and what is not possible, so as to make the better decisions on like when you're doing a project. You might, if you know the limitations, you might design things more promptly than if you don't consider the limitations. So if we think of the challenges in quantum computing in general, so like as we saw in like a simple experiment that we did with George Oracle, that ideal quantum computer was giving 1-1, but the available quantum device would give something different, but then there's an error. So these errors are increasing. So as Kitmin also mentioned, so to mitigate these errors, people are looking at something like in normal, if we think of classical information theory, how these errors are mitigated, it's through redundancy. So what we do, we will, if we want to get 1 qubit, we will have more qubits to support that. So to have 1 logical qubit, we will have to have many physical qubits. So these kinds of error mitigation techniques would be, and then different technologies might be having different errors. So you will have to choose the technology based on the application. And then there will be issues with scalability, like everyone on the race of quantum computers, they are trying to make it scalable, like in the sense increase the number of qubits, but how well we can sustain with that, like once we have a state, it will how to which, like what time, like what is the time interval that we could keep that state as it is, and it might interact with the environment in the real world. It's not noiseless. it's noisy, so it will interact with the environment and it will change the state. So these kinds of things are, we have to be like careful when designing scalable systems, and when we want to connect different devices, and when we want to connect different large number of qubits, how to make the circuit topologies, and those how to make those qubit topologies. Those things are interesting things to look at. So in quantum computing today, people are on a race, like looking for all these things. Like everyone is looking at what are the alternatives, or what are the things that you could look for in improving these kinds of things. So if you are interested in quantum computing, you might be someone who would try to make this better, in a sense of improving some of the things, or else finding out some kind of new quantum algorithm, which is like one of the other section that you have to you can look for. And it's also worth to mention that quantum in general is a very multidisciplinary field. So you might be able to contribute to this field in different ways. Either you are in different like some other completely different field, like nowadays even computer scientists, physicists, like mechanical engineers, even chemists, and those kinds of, a lot of material science people, and all those people get together in looking at quantum in developing quantum technologies. So this is a multidisciplinary field, so there are a lot of opportunities behind that, and even I'm also learning them, or else like so if there are no other questions, if I can hand over to Kitmin. If there's any, we can discuss. Thank you for your attention all throughout like this afternoon for like 2 hours here.
So thank you, Teshani. You must be very tired by now. And I think it is very early in the morning, right? So like 3 a.m. or
Yeah,
something.
it's around 4:30 a.m. now.
Yeah, so if you have any questions from the whole thing, you can ask. So people have not asked too many questions up until now, right? So I don't know whether people didn't ask because they understood everything or they couldn't understand anything. So the thing is, right, so every session that we did up until now, right, so there are many resources available everywhere, right? So so you can look at all these things in YouTube and in different places, but what the course like this truly does is basically it allows you to ask questions, right? So if you have any questions, I think because in a YouTube video, if you have a question, you can't ask, right? So the advantage of having a session like this is you can actually ask questions. So you can even ask now, or if not, you can send us an email, and that will be all fine. So yeah, so if you don't have any questions, we can end the thing. But where is Kitmin? Is Kitmin here? Is it 4:30 for Kitmin also? Is he asleep?
I think it's one something there.
So any of the audience, if you have any questions, you can ask us. So the session will be available in YouTube. We will upload this to YouTube in some time. Okay,